Hello, my name is Jason Schnackenberg. I'm sorry that I am unable to present in person due to being on travel this week for work. Since my co-presenters just walked you through the capillary effects and phase boundaries for unary systems, I would like to take some time to briefly introduce some concepts with phase boundary shifts in binary systems, particular the phenomenon of Ostwald Ripening. The learning objectives for this discussion are the basic understandings of differences between unary and binary capillary effects. What is the Ostwald ripening process? How the Ostwald ripening process is modeled? And where do we see this process occurring? So just briefly on how capillary effects in binary systems are similar to unary systems. Capillary effects can still cause large shifts in phase diagrams, and surface tension and vapor pressure are still really driving forces in these shifts. But they're different in binary systems because they can include a lot more effects, such as chemical potentials between compounds and miscibility of one compound in another compound. And that brings us to the Ostwald ripening process. And to really break this down, if a number of nanoparticles or droplets of one compound are dispersed in another compound, the large particles will increase in size and the small particles will decrease in size. And this is a different process than particles convalescing. This isn't little particles coming together and becoming big particles. And this is because the smaller particles have a higher surface area to volume ratio. They have higher surface tension and interphase energy than the larger particles. And this is the overall mixture just trying to lower its energy. And this process is a little bit easier to understand if you see it. So this is a simulation model of this process that I found that looked like it was a good video. And as you play this, you can see that the smaller particles aren't bumping into the bigger particles. They are disappearing in the solution, and the larger particles are growing. And so they're actually dissolving and recrystallizing with the larger particles here. The general form of the Ostwald ripening model is this equation right here. And in this equation, we have A is the radius of the particle or drop. So this is showing the change in that radius over time. And D is the diffusivity. V is the molar volume. Gamma is the interfacial tension. V is the volume fraction. R is R. T is temp. Let's see, delta is the continuous phase thickness, and AC is the critical radius of the drop. So the main takeaways that you have from this equation are that when A over AC is less than 1, this dA versus dt over dt is negative, and the particle is going to be shrinking over time. When A over AC is over 1, this is going to be positive, and the particle is going to increase over time. Also worth noting is that the worth of change is dependent on the temperature and the diffusivity. So this is going to be different based off how miscible different compounds are within each other and how hot they are. So back to a couple examples on this, since this is something that just can slowly occur over time. This is why when you have ice cream, it's smooth and creamy when you first buy it, and after it sits in your freezer, it has the exact same amount of water in it, but the crystals get larger over time, and eventually you can even see them, and it becomes hard. Another example of this that you might see is in rocks, Rocks that cool slowly, like granite underground, will produce very large crystals, and rocks that cool very quickly because they come out of the ground will produce very small crystals. And this has a lot of other important um, implications in metallurgy and heat treating and stuff like that, but these were some examples that I liked. Anyway, that's all I really have time for in this short video. Thanks for watching, and I hope you learned a little something about the capillary effects in binary phase diagrams and the Ostwald ripening process.